Hello guys! Today we are dealing with the concept of correlation. We will try to understand what it means and how to interpret this coefficient. Take a look at the graph. Here we have the Cartesian coordinate system with x-axis and y-axis. And you see the scatter plot, the points on the graph that depict the object that we measured, which have x characteristics and y characteristics. Then if we consider the average of x and the average of y, we will have them depicted on the graph like this. And let's consider the following transformation. X sub I centered, this circle at the top denotes the centering procedure. So we will just subtract from each x sub I its average. The same we do for y. So y sub I centered will be equal to y sub I minus y average. And then if we apply this transformation to our data points, we are shifting this center of this scatter plot to the origin of the coordinate system if we denote on x-axis x centered and on y-axis y centered. It would look like this. You see, we just shifted the origin of the coordinate system into the center of this scatter plot, of this cloud of points. Next, let's consider the following sum. The sum of products of corresponding x and y coordinates for each object, but of course already centered. If we take a look at the first quarter of the coordinate system, this one, you see if we just multiply the corresponding x and y for each data point, we get a positive value. If we take a look at the third quarter, we also will get a positive value because the x would be negative and y would be also negative. And the negative value times negative value will give us a positive value. And only in the second or the fourth quarters, we will get the negative value. If we multiply x by y, because here x is positive, y is negative, and in the second quarter, y is positive and x is negative. So clearly in our case, we see the positive dependence, and this sum will be clearly positive because you see how many data points we have in the first and the third quarters and how few we have in the fourth and then the second quarter. So this thing shows that whether the relation is negative or positive. So if this sum of products is positive, that means we can count on the positive relation between x and y. If this one is negative, so that means it has negative relation, because if the scatter plot is directed like this to the negative direction, so we would have more data points in second and the fourth quarters. And if we have no relation between x and y, we would have just a non-directed cloud, and all these products that are associated with the data points in all four quarters would just cancel out, because we would have the some number of data points in the first quarter, some number in the second, some number in the third, and in the fourth. Since two of them are negative, two of them are positive, they will just cancel out and this value would be close to zero. Next, take a look at this normalizing constant. This is how we denote the correlation coefficient, R sub xy. So the correlation between x and y. And the correlation coefficient is a bounded indicator that varies from -1 to 1. It's easy to interpret. If it's close to -1, that means we have a very strong negative relation. If it's close to 1, that means we have a very strong positive relation. And if it's close to 0, we would rather say that there is no linear connection between x and y. So what this normalizing denominator does is just bounds the whole fraction to fit in this very range from -1 to 1, so that we can compare different data sets and the strength of the relation between different variables. Since what we have in the numerator is unbounded, so it can take up any value from -infinity to infinity, two correlation coefficients wouldn't be comparable if we don't divide it by the normalizing constant. So this constant we need to be able to compare different data sets, different correlation coefficients. Now, if we substitute x and y scaled with the initial values that we had, we would get the formula like this. You see, that's the same thing, just substituted x scaled and y scaled with x sub I minus x average and y sub I minus y average. And this can be also simplified to this analytical form. So the correlation coefficient would be equal to xy average minus x average times y average divided by the square root of the product of two variances, variance of x and variance of y. So since this is the variance of x, this is the variance of y, the square root would be just the standard deviation of x, standard deviation of y, and what we have in the numerator would be the covariance of x, y. So this is just the representation of the covariance between x and y. That's why we can simplify the correlation coefficient as covariance of x and y divided by sigma x and sigma y. And this, you gotta remember, this is called Pearson correlation coefficient. Now let's show why do we pick exactly this form of the normalizing constant. And we take the numerator, but we denote as an a sub I and b sub I, so that could be any numbers, and we divide it by the square root of some a squared sub I and times some b squared sub I. We want to prove that given any numbers, any values of a and b, we have this inequality fulfilled. If we square this inequality, we will get the equivalent representation. So this inequality means that this one also holds. So if we just square it up, we would have then sum of the products of a sub I and b sub I squared is less or equal to the sum of a squared sub I times sum of b squared sub I. This inequality in mathematics is called Karshi-Schwartz inequality. Let's briefly show the proof for this inequality for n equals 2. It can be, of course, easily extended for any n, the number of observations that we have. Let's take a look at the right part of the inequality. And you see the right part of the inequality is just the sum of these four terms. You see, if we just write all the terms explicitly, given that n is equal to 2, we will have this a sub 1 squared times b sub 1 squared plus a sub 1 squared, b sub 2 squared, plus a sub 2 squared, b sub 1 squared, plus a sub 2 squared, b sub 2 squared. So we sum them up, and that would be exactly this part of the inequality. Let's go to this one. And this one would also have four terms. That would look like this. So this part of the inequality would be the sum of these four terms. And you see that some of them from the left side are equal to some from the right side. That's why we can cancel them out. And now we are left just with four terms. Thus, the inequality for n equals 2 can have the following shape. This one. And if we simplify this equation, we will get this one. You see? That would be just the square of difference. And we know that the square of difference, given any values of a sub 1, b sub 1, a sub 2, b sub 2, would be greater or equal to 0. What completes the proof? That's how we showed that this normalizing constant actually bounds this fraction to vary from -1 to 1. Here let's consider brief examples of the shape of different patterns and their corresponding correlation coefficients. You see clearly, the first graph, we don't see any dependence between x and y. That's why the correlation coefficient is equal to 0. The second scatter plot already shows some dependence. You see, in the first and the third quarters, there are more data points than in the fourth and the second. And here the correlation coefficient equals 0.5. If we take a look at this graph, the dependence grows stronger. And it is reflected in the correlation coefficient as well. It equals to 0.8. And finally, you see for the correlation coefficient 0.95, we have very strong relation of x and y. Here we give a very brief definition of what correlation is. In statistics, usually correlation or dependence is any statistical relationship. Doesn't matter whether it's causal or not between two random variables. It's very important to note that correlation doesn't imply causality. If two variables correlate, it doesn't necessarily mean that one causes the other. To understand the causality between two variables would require additional causality detection analysis. Pearson correlation coefficient is a measure of linear correlation between two variables. What is also very important to remember, if you take a look at the graphs below, you see that the linear connection is clearly marked with the corresponding Pearson correlation coefficient. You see, if the connection is linear, doesn't matter what the slope is, the correlation is 1 or -1. But if we take a look at the bottom row, we see, though the data is clearly dependent, the Pearson correlation is still 0. So that means if you get 0 Pearson correlation coefficient, it doesn't necessarily mean that you have no connection between x and y. That clearly states that it doesn't have linear connection, but there may be some other one. That's why it would maybe sometimes require additional analysis of your data. So, I guess that's it for today. Watch our next videos for more detail.